Good morning to one and all gathering here. Welcome back. Now we are entering in the first session of fourth day, which is based on Basics of Approximation Theory by Dr. Asif Khan, Aligarh Muslim University, Aligarh, Uttar Pradesh. Now I would like to request Dr. Asif Khan sir to take over the session. Please sir.
Thank you very much. Okay. So is it visible, this PPT?
Yes sir, it's visible sir.
The title of my talk is Basics of Approximation Theory. At in this 1 week virtual refresher program on Applied Mathematics at Department of Mathematics of M. Kumarasamy College of Engineering. So here, this is the basically outline of my talk. I will start from the basic definition of approximation theory, some of the applications of approximation theory, and broadly we will see that approximation theory is divided into theoretical and constructive approximation. So in theoretical approximation, we basically used to talk about existence and uniqueness of best approximation, and in constructive we used to construct best approximation, we used to estimate error, rate of convergence, etc. So we will see approximation in both metric spaces and non-linear spaces. What we mean by best approximation is its existence and uniqueness. Here I will explain both. I mean the mathematical definition and the geometric idea about this existence of this best approximation and uniqueness. After that, I will come to the central theme of approximation theory called Weirstrass Approximation Theorem, and I will also discuss one of the constructive proof of it by Bernstein, based on probabilistic approach. However, Weierstrass' original proof is based on convolution technique. And then this work is extended. Actually, the proof by Bernstein is in 1912, was given by Bernstein in 1912, and later on it is extended to by Korovkin and his team around 1950 for positive linear operators. So I will come to that one, and after that I will discuss with the help of quantum calculus some of the standard operators which are very well known. Basically, quantum and post-quantum calculus are extension of quantum calculus, and under some assumption, it will give you all the results of your classical calculus. So for that, I will discuss Laplace and Phillips. This one is a basically rational operator, and this one is Phillips operator, polynomial, and then it's post-quantum generalization given by supervisor. And then another one, post-quantum analog of Laplace-Bernstein operator. It has various applications in computer geometric design given by Khalid and Royal from JNU. So, and then in the last, I will discuss some of the recent work. I mean, application of Bernstein type basis in computer geometric design, some work in image processing. I mean, application of these operators with the help of pseudo-linear approximation in image processing. And if time persists, I will also discuss this statistical convergence. So, as I told that approximation theory is broadly divided into theoretical and constructive approximation. Constructive approximation deals with computational practicalities, precise estimations of error, and so on. Whereas theoretical side is more often concerned with existence and uniqueness questions. And now, question is why approximation theory? See, there are several reasons for studying approximation theory and methods, ranging from a need to represent functions in computer calculations to an interest in the mathematics of the subject, and especially work in numerical analysis and in mathematical software is one of the main links between these two extremes. For its purpose is to provide computer users with efficient programs for general approximation calculations in order that useful advances in the subject can be applied. There are several more reasons, but I'm not going to see. So, approximation theory, the key idea for approximation is replacement of something complicated with something simple. Simple in the sense easier to compute, easier to represent. For example, we already know that pi is an irrational number having non-terminating and non-recurring form. But when it comes to its implementation using computers, we have to limit, we have to truncate rest of the terms. And already see, I have seen that one of the invited speaker has already covered this topic. So the computer is limited in its ability to represent the magnitude and precision of a number. So somewhere we have to truncate rest of the terms, I mean after 2 digit, 4 digit, 12 digit. So because again, because we will later on see that actually we or human beings cannot deal with infinite things. Theoretically it's okay, but when it comes to applications using computers, we have to limit, and we have to deal with only finite things. That finiteness may be in terms of length of interval, that finiteness may be in terms of collection, that finiteness may be in terms of dimension, depending on the type of problem. And this already we know that replacement of complicated functions using Taylor series. So when we truncate Taylor series, we will get polynomial. A replacement of Fourier series by partial sum. Again, finiteness will play a role here. Other examples like data compression of large data sets into smaller data sets. And this, divided difference. Divided difference is again approximation of derivative. For example, if someone wants to construct a model based on Newton's second law, then in that acceleration derivative of velocity, one has to be approximate it with the help of divided difference. Similarly, difference equation which we are using in our numerical analysis is approximation of differential equation. So these are some well-known examples. Now let us look at some examples in vector spaces. So we know that small LPN, basically small LP is the notation used. Actually, all these notations are already used by one of the experts. So I am directly coming to the main one. See, LPN is basically collection of all those sequences whose P absolute sum is finite. So if look at every sequence has this property, all those sequences, here we are constructing sequences with the help of natural numbers. So all the sequences has this property that their infinite sum is finite, their P absolute sum is finite. Now look, when you want to implement it using computers, so we cannot do this infinite sum using computers. So those who are working with the help of MATLAB, or they already know. So now can you look at some of its subspaces, from which we can approximate every element of this space, I mean every sequence. So that is what we have already studied in our in functional analysis, and in our post-graduation courses. We already used to study about this type of subspaces. See, collection of all those sequences in which only finitely many xk are non-zero. So I will come to the basic of this one, that later on we will see that this space is basically dense subspace of this one. I mean every element of this space can be approximated by the elements of this from this subspace. Okay. So again here finiteness will play a role. Actually I am looking it from the applied mathematics part, how to implement it. That is why I am emphasizing more on this one. Now similar is, let us take the capital LP spaces, the space of functions. I mean the functions from R to C whose absolute P sum integral is finite. So if you look at this space, I mean look at the members of this space, these functions, then its domain is R. I mean unbounded interval. Its domain is unbounded interval. So again, when we know that computers cannot handle with infinite length of interval, so again we have to look at its subspaces, I mean some members from this space, by which we can approximate every member of this space LPR. So later on you will see that with the help of compact support, this CCR, I mean space of all continuous function with compact support, is a subspace of this one, and with the help of this subspace I can approximate, I mean every element of this LPR, capital LPR, can be approximated from the members of this CCR, I mean space of all continuous function with compact support. So, or you can in mathematical work you can say that this space is dense in LPR. For all 1 less than equal to P is less than infinity. Actually, compact support is defined as closure of the set. Compact support of a function is defined as closure of the set at which fx is non-zero. And if this compact support is bounded, so we know that every bounded subset can be contained into an interval of finite length. Okay, so this is the reason why we are reducing our length of intervals to a bounded interval. So again, here this finite length, finite word is going to play. Now, the basic of actually the history of approximation theory. This started when in 1853, the great Russian mathematician P.L.G. Weierstrass, while working on problem of linkages, devices which translate the linear motion of a steam engine into circular motion of a wheel, raised the following question: that given a continuous function f on closed interval ab, can we represent f by a polynomial of degree at most n in such a way that the maximum error at any point x in ab is controlled? and or in particular, is it possible to construct a polynomial in such a way that this error, maximum error, is minimized? So if you look at this one, then this is what requirement under sub norm, under infinity norm. This is what requirement under infinity norm. Maximum of this where x belongs to AB and then minimizing it. So I will come to that one. So this problem raises several questions. I mean, why should such a polynomial even exist? If it does, can we hope to construct it? If it exists, is it also unique? And what happens if we change the measure of the error? I mean, in place of subnorm pointwise error, what will happen if we take the average error? So I will come to this error concept one by one. Now here, let me start from this metric spaces, approximation in metric spaces. So we know that any non-empty set equipped with a distance function d. Metric space, basically your metric space is any non-empty set equipped with only one tool distance function. So it basically it will measure the goodness of an approximation, because one of the basic properties of metric spaces is that it has a distance function d. Now if I say that, suppose x and y belongs to this metric space x, okay, belongs to this metric space x, then what will this term lambda x plus 1 minus lambda y indicate? Suppose lambda belongs to closed interval 0. Will this term make sense? So obviously these type of things in general in metric space we cannot talk. Why? Because the vector space operations are missing. This is scalar multiplication. This only we can talk in non-linear spaces. I mean, because non-linear spaces are defined, its domain is vector space. So there we can talk. Here we have only one tool. So how to do approximation with only this distance function? So that I will come. Here I have not written the definition of metric spaces and non-spaces, because already most of the I have seen that the various invited speakers have already covered that one. So approximation in non-spaces. Okay. So this one is basically how, suppose x is any metric space equal to the distance function d, and y is its subset. Y is its subset, and suppose there is an element, say x naught, outside y, or okay, here I have denoted it by f. Let me call this element as f. So question is that what will be the best approximation from this set y which approximate this f? So what we need to do, we need to compute the distance, because already on this set x we have the distance function. So with the help of this distance function, try to compute all distances between a and f, where a belongs to y. So see, we are writing here infimum of d of af. Basically, this one is stand for this one, where a belongs to y. So first of all, try to compute distance between every a and f. We already know the distance is a non-negative real number, because d is a mapping from x cross x to r plus union, 0 to infinity. X union 0 to infinity. So again, it is going to be always a real number. So you can talk of it. So after computing all those distances, take its infimum. And how infimum is defined? Basically, infimum is of this set. You have to look at all its lower bound, and among all lower bound, the greatest one is called infimum. So if for those a at which this infimum will be achieved, those will be called as the best approximation. So this is how we will do approximation in metric spaces. So let me make it more clear with the help of some example. We already know that, see, this one is a real line, and suppose I have x naught equal to 3 here, x naught equal to 3. This element I need to approximate from its subset open interval 0, 1, from its subset open interval 0, 1. Question is, what will be the best approximation to this element from this set? So we already know that, see, if you try to compute d of this a and f, okay, a and x naught, d of a and x naught is 3 here also, x naught is 3 given, and a belongs to, say, this y, a is coming from this y. So look at all such possible distances and take its infimum. Look at its infimum. So you can see that from this element, say 0.5, the distance of 3 to 0.5 is 2.5, and see from the next element, from here you will have some other real number. So basically you need to find the infimum of this set. And see, if I say that suppose b is equal to open interval 2, 3 or closed interval 2, 3, then what will be infimum of this set? suppose B is equal to open interval 2, 3, then what will be the infimum of this set? So obviously infimum of this set, for that what we need to do? We need to find its lower bound first. So all real number less than equal to 2 are going to be its lower bound. So I can say that lower bound of set B is basically all x less than equal to 2, and among this the greatest one is 2. So I can say that its infimum is 2. So if you collect the distances from these three for all a belonging to this open interval 0, 1, then you will find that this infimum comes out to be 2. This infimum comes out to be 2. Now infimum is achieved, but question is what will be that a at from this interval? What will be that a from this open interval 0, 1 at which this infimum will be achieved? So you can see that the distance from 1 to 3, I mean infimum will be achieved for 1, but here I have taken the open interval 1, open at 1 is not included in this one. So there is no element from this open interval 0, 1 from this subset at which this infimum is achieved. So I will say that best approximation will not exist. So what will happen that in place of open interval 0, 1, if I choose closed interval 0, 1, then best approximation will be 1. Then so somewhere you can observe that the role of closeness is there for existence of best approximation, and in fact for stronger cases I can say that if you replace it with the compact set, then best approximation is guaranteed, because compact sets are always closed and bounded. And bounded we need because we have infimum here. Bounded we need because we have infimum here. Because infimum, whenever see we will talk of infimum and supremum only when bounded. I mean it is bounded. Otherwise, infimum supremum may or may not exist. So this is why. So I will come to that standard theorem. Now, so somewhere we have seen that closeness is related for existence of best approximation, and then we will generalize it. Now, second, for existence, suppose let me replace y by closed interval 0, 1 union say 5 to 6. Okay. So from this subset, what are the best approximation for x not equal to 3? So you can see that this one is from 5 to 6. This already I have taken closed interval, so obviously best approximation is guaranteed here. 0, 1. See, actually, what I want to say that the name is coined as best approximation, but it may or may not be unique. So I will try to explain with the help of simple examples, assuming that all of we are new to this topic, and then I will extend it to abstract spaces. So if you observe, then best approximation from 3 is, look, 1, 2, okay. So best approximation, I mean a0 equal to 1 and 5 are its best approximation, because at both the same infimum will be achieved, 1 and 3. So you can see that 1 and 5 are we have two best approximation for x not equal to 3 from this set, from this subset. So now question is that which type of subset we will choose that this best approximation becomes unique. So if you replace this y by some convex set, you can see that this set is not convex. So if you replace this set by some convex set, and in more stronger condition, we will see the definition of strict convexity. That if your set is strictly convex, then we have the unique best approximation. So I hope this one is clear. Am I audible to everyone? I think yes. Can you hear me?
Yes, sir.
Okay. Actually, I thought that. Okay, let me share it again. I think. Actually, it's one-sided communication, so sometimes it feels that I have lost connection. Okay, so let me share it again. Is it visible?
Yes, sir.
Okay.
Yeah.
So now what I want to say here is that similarly you can extend it to R2. Now, so if Y is a compact set, if Y is a compact subset of X, then any F belonging to X for any, there exists at least one best approximation. And if you look at the definition of compact set, a set is said to be compact if every open cover has a finite subcover. So compact is again some sort of abstract generalization of finiteness. However, every compact set is closed and bounded in metric spaces, I mean in non-spaces, but converse need not be true. For example, on R, you have seen that if you take discrete metric, then it is closed and bounded, but need not be compact. In topological space, we will not talk of the, even a compact space will not be closed, and we will never talk of boundedness unless it's metrizable. So now look here, how to define best approximation in non-spaces? See, so Chebyshev's problem is perhaps best understood by rephrasing it in modern terms. A norm on X induces a metric or a distance function by setting distance of x y equal to norm of x. So we know that this, with the help of this norm, I can always have the metric. So in non-spaces, because the domain of norm is a vector space, so there we have linear structure. There we can talk of scalar multiplication, vector addition, all that. So given a subset Y or even a subspace of X, and so what will be the best approximation to any X belonging to X from this Y? So again, this is that you need to compute the distance. This X is fixed, let me call it X naught, and you have to vary this Z on whole Y, compute these distances. This with the help compute this norm and look at its infimum. So for that Z at which this infimum will achieve, we will call that as one as best approximation. Now, so this is basically requirement for this is one of the theorem that suppose Y we have. I will explain from where we have this one. So if Y is a finite dimensional subspace of a non-linear space X, then there exists at least one best approximation to X by elements from Y. Actually, you see, we already know that finite dimensional non-spaces are complete, and if Y is finite dimensional subspace of a non-linear space, then Y is always closed subset of X. So again, we have, so using this is a theorem. Now before coming to other spaces and its geometrical explanation behind this existence and uniqueness in terms of walls, let us quickly revise this one, the types of LP norms present on CAB and Rn. So in most of the, I'm talking about LP norms, not LP spaces. So in most of the approximation problems that we consider, F and Y are the space are in the space CAB. Y is subset or subspace of CAB, and F is from CAB, which we need to approximate. See, this F, basically I am using, earlier I have used this F as a member of set X. That set X may not be, maybe collection of polynomials, maybe collection of functions, maybe collection of matrices, maybe collection of sequences. So here in particular, F represents continuous function, because CAB we already know that is the set of all continuous real valued functions that are defined on closed interval AB. So occasionally we turn to discrete problems where F and Y are in Rn, which is the set of real M component vectors. Both of these spaces are linear spaces, we already know, and we have on any set or on any vector space we can define various norms. So here I am going to consider these three norms, norm 1, 2 and infinity norms, because frequently we are going to use this in our calculation. So we know that LP norm for this CAB, on this CAB is defined as this one. You have to take its absolute Pth absolute value and then integrate it, and then take its Pth root for all 1 less than equal to P less than infinity. And if in place of this we have Rm, then you have to take its component wise. Then LP norm is given by this. You have to take absolute sum of all components, sum it, and then its Pth root. And infinity norm, we already know infinity norm, see, maximum mod of fx. So somewhere you will find maximum in case of CAB, somewhere you will find infimum, supremum, because CAB is already a complete space with respect to this norm. However, with respect to integral norm, it is not complete. So you can see that the infinity norms on this expression on CAB is defined as this one. You have to take mod absolute value of fx, and then for each x, and then take its maximum. And on Rn respectively, you have to take absolute value of each component for I running from 1 to m. So this is how this LP norm is defined. Now I want to give you the idea, geometrical idea, that how from where we have existence and uniqueness. Let us look at its geometrical idea. So in this case, when f and y are contained in non-linear space x, and when we require the best approximation from y to f, it is sometimes helpful to think of the balls of different radii whose centers are at f. See, the balls of radius r is defined to be the set. This is notation for closed ball. So closed ball with center f and radius r is defined as a collection of all those g from the non-linear space such that norm of f minus g is less than equal to r. If you remove this equality, we have the definition of open ball, and if we have only equal to, we will get boundary of open ball. So now, for any f belong to x minus y, if y is finite dimensional, then you will see that this infimum will be achieved. This infimum will be achieved. So with the help of norm, one can always construct balls. With the help of norm, similarly with the help of metric, because norm induces metric. So again, with the help of metric, one can always construct balls, because in metric space, similar result, will hold. So let us try to understand it with some example in non-linear spaces. For example, suppose X is the two-dimensional Euclidean space R2, R cross R, and that we are using the 2 norm. We are using the 2 norm, Euclidean norm. Let F be the points whose components are 2, 1. I want to approximate this point, this member of R2 from these subspaces. Actually, this one is the line passing through origin. If you look at this is the collection of all points in R2 lying on another line. So look at its geometrical view. See, this is 2, 1. This is 2, 1. This I need to approximate, and your subspace y is this one. Actually, as I told you earlier, that suppose X is a non-linear space and y is subset or subspace of X, and any f is here 2, 1. I need to approximate this 2, 1, and this y is basically this one, this line, subspace. And we know that any line passing through origin is a subspace of R2. So now what will be the best approximation from this set? What will be the best approximation from this set to this 2, 1, to this element f, denoted by 2, 1. So what we will do, the idea is that start increasing the radius of the ball with center at f. Look at its boundary. Actually, in R2, the open balls are open disk. And the closed balls are closed disk. But what we need to look, start by taking f as center, start increasing the radius of the ball. So at the point when the boundary touches, when the boundary touches this subspace, this will be basically your best approximation. And you can also see that this best approximation is going to be unique, because in R2 this one is the curve. So at least either the subspace, you can see that this subspace is containing the linear segment. So this is not strictly convex. But look at the balls here. If you start increasing the balls here, then this one is curved, so it is going to touch at only one point, and this is why this is your best approximation. So so what we have observed from here, and also we know that in the 1 norm, 2 norm, and infinity norm in R2, the balls, already one of the expert has covered this. If you recall, in the first lecture, I think one of the invited speaker has already covered this, that what will be the nature of balls in R2 with respect to 1 norm, 2 norm, and infinity norm. So you can plot it if you want. You can do it. See, if the 1 norm, if you want to draw the balls in 1 norm, ball with center say 0 and radius r, ball with center 0 and radius 1. Okay. Actually, non-spaces we used to construct balls with center origin and 1 unit radius. The reason is that once you know the ball of unit radius, you can easily translate or dilate it. In non-spaces, which you cannot do in metric spaces. The reason is that non-spaces, its domain is vector space, so you can do all that linear type calculations. So ball with radius 0 and radius, ball with center 0 and radius 1 is defined as basically collection of all y belonging to R2. Actually, this pen is not working here. Y belonging to R2, such that distance between x and y is less than 1. Distance between 0 and y is less than 1. Now, if you recall the norm, this 1 norm, basically this is mod y1, comma mod y2, Suppose y is the component having its component as y1, y2 in R2. Obviously, its member will be two tuples. So mod of y1, maximum of mod of y1, y2. So it has to be less than equal to 1. If you want to make the closed balls, then mod of y1 less than equal to 1. So you will find that, sorry, what I, okay, 1 norm, sum of yi. I mean, simply I can say that y1 plus y2 must be less than equal to 1 for closed ball. D of xy less than equal to 1 in norm 1. So assuming this one as y1 and this one as y2, if you try to plot it, so let us take y1 y equality sign here, and in first quadrant we have y1 plus y2 equal to 1. Since it is symmetric in y1 as well as y2, so it is going to be symmetric about y1 axis as well as y2 axis, so you will get this one. Similarly, if you take the 2 norm is basically Euclidean norm. So in this one, you will get y1 square plus y2 square less than equal to 1. So you will get unit circle and its interior. But if you take equality sign, you will get this boundary. Similarly, in infinity norm, we have maximum of mod of y1, y2. And for unit ball, that has to be less than equal to 1. And for boundary, it must be equal to 1. So y1 equal to 1 means mod y1 equal to 1 means y1 equal to plus 1 and minus 1. So it is a line parallel to y2 axis. And similarly, when mod y2, so we will get this type of open balls. So you can see that what I want to say here is that you can see that with respect to one norm, again its boundary is containing the line segment here, so it is not strictly convex. Again, with respect to infinity norm, its boundary is going to contain the line segment. But for all other norms lying between 1 to infinity, all LP norms, you can see that its boundary is convex. I mean strictly convex. So for that you will get the unique solution, but for 1 and infinity, you will not, I mean best approximation may or may not be unique. Now I want to sum up all these results here. So these are the unit balls of the 1, 2 and infinity norm. And we already know that in non-linear space, once you have the unit ball, take scalar multiplication with r radius. So unit ball here, you can translate it to, why we are doing this, because we know that in non-linear spaces, suppose this one is the unit ball with center origin, and suppose there is any element x in non-linear space, whether it is inside the ball or outside the ball, once you divide it by its norm, it will be always on the boundary. It will be always on the boundary of the ball. Okay, and when you take r less than 1, it will be inside. When you take r greater than 1, it will be outside. So what will happen that, and you know that why it is on the boundary, because already we know that result, that norm of alpha x is equal to mod of alpha into norm of x. So when you take its norm, basically this one is the scalar quantity, will come out, and we have one here. So this is the reason why. So using this property and property of vector spaces, once you know the ball with center 0 and radius 1, one can easily translate it, dilate it. I mean, you can contract it or you can magnify it. So with the ball with unit radius can be shifted to ball with center x and radius r. This is why reason that I have taken here ball with center 0, 0 and radius 1. So the shape of the balls in two-dimensional spaces for the 1, 2 and infinity norms are interesting, because they indicate some of the implications of the choice of norm. The boundaries of the 3 unit balls centered on the origin we have already shown. Okay. Now look here. The 2 uniqueness theorem which I am going to state that are given next are self-evident if one takes the geometric view of the best approximation. We recall that a ball with center f is allowed to grow until it touches the set y of approximating functions, and then the radius of the ball has the value at which norm will be achieved, infimum will be achieved. The 2 theorems state that there is only one point of contact between the subspace or subset and the ball, closed ball, boundary of the closed ball, if the boundary of either y subset, I mean subspace, or this ball, closed ball, is curved, or if both sets are convex. So after combining this, see, this one is the mathematical definition of strictly convex space. A convex set y is said to be strictly convex if its boundary does not contain a line segment. If its boundary does not contain a line segment, or you can say that only convex subsets of boundary are the empty sets and the singletons. And any norm on a vector space X is, when we will say that any norm, when we will say that this space X is non-linear space X is strictly convex. So with respect to the norm present on it, if X is not equal to Y, and if lambda X plus 1 minus lambda Y norm is less than R, then basically it is not going to contain, I mean, then this space is going, will be said as strictly convex space, or in other words, we can say that X has a strictly convex norm if and only if the triangle inequality is strict for non-parallel vectors. From the previous one can derive this one. So where X is not equal to alpha Y and Y is not equal to alpha X for all alpha belonging to R, and norm of X plus Y is strictly less than norm of X plus norm of Y, then we will see that X has strictly convex norm. So now I would like to sum up what we have seen till now. That see, if Y is subset of X, this condition is on subset of X. Okay, if Y is subset of X and it is closed and strictly convex, then any F belonging to X minus Y, we have at most one best approximation from Y. And this one is on the whole space X. This one is on the subset. This one. So if X has strictly convex norm, then for any subspace Y of X and any point X belongs to X, there exists at most one best approximation to X out of Y. There exists. So these are the two basic results for existence and uniqueness. So if someone is interested, one can follow the book by M.J.D. Powell, Approximation Theory and Method. That is very good book in which all these details are given. Most of the things I have collected from that book. Okay. Now, mathematically, one can also verify that why the space CAB is so interesting with respect to uniform norm. I mean, with respect to infinity norm. Why uniform norm? Basically, whatever convergence you will choose, you will do in this one. That comes out to be uniform convergence. So, sometimes infinity norms are also referred as uniform norm. So, you can see that the space CAB is not strictly convex because triangle inequality is not satisfied. Why? Let me restrict closed interval AB to closed interval 0, 1, because once you know the result on 0, 1, you can easily extend it to closed interval AB by using this map, by taking composition with this map 0, 1 to AB. See, if you take any X here, then you can easily translate A plus X times B minus A. B minus A plus X times B minus A, because when X is 0, we have A here, and when X is 1, this A get cancelled out, we have B here, and this one is increasing. So whatever X you will choose in between 0, 1, it will give associate to a real number in between A to B. So by combining this one, whatever result you have on C01, it will be extended to CAB. Now on C01, if we have fx equal to x and g of x equal to x square, so we already know that the supremum of x on this closed interval 0, 1 is 1. Supremum of gx square is again 1, and supremum of norm of f plus g on x plus x square on 0, 1 is again going to 2. So your triangle inequality that 2 is less than 1 plus 1 is not satisfied. I mean, norm of f plus g is not less than strictly norm of f plus norm of g. So this is the reason why CAB is not best approximation in CAB may not be unique. And you know, in real life problems, whenever you want to mathematically write a problem, you need to take help of functions. And if your function is continuous, then obviously it will be member of the CAB. And see, if your best approximation is unique, then there is no problem. But if best approximation is not unique, then the spaces are become interesting. Why? Because in that case, you can construct several best approximation, and then you can compare the rate of convergence and I mean trade-off type of things you can study. So this is why this type of spaces are, this space C01 is more interesting. And also there is one more result on error. I will relate the error in norm 1 with respect to norm 1, norm 2 and norm infinity. There is a relation which also makes this C01 space more interesting with respect to infinity norm. I will come to that one. Now, also in first lecture, one of the experts has also already covered this, that what will be ball with respect to subnorm, I mean uniform norm with center at 0 and radius epsilon. So we know that, see, the members of this space, here 0 means 0 function, because this is the space of function. So here 0 means 0 function. So if you look at the balls I mean with center f and center 0 and radius r. So okay, here we have epsilon. So balls with center 0 and radius epsilon is collection of all those functions, say g, belonging to C01, such that norm of, I mean you can take, because from norm we will get metric. So you can write norm of g minus 0 minus g is less than epsilon, and this norm in C01 is basically maximum supremum of 0 minus g. So what from here you will get that function g must lie between 0 minus 0 plus epsilon and 0 minus epsilon. You need to look at all those functions g, and already supremum is there. So you have to plot this 0 plus epsilon, 0 minus epsilon, and look if f of x is equal to x square. Then if I take x equal to 2 here, then f of 2 will be 4. So once you substitute the value of x here, it will be a real number. So what we are trying to do here is that y equal to 0, basically this 0 function is y equal to 0, and y equal to 0 is x-axis, it's your x-axis, and since we have restricted our domain to 0 to 1, so in this one is your 0 function, this one is your 0 function, and at each point you have to add epsilon, 0 plus epsilon. So you will get a constant parallel line to this one, 0 minus epsilon. And if you are okay, for open ball we have strictly less than sign. So this is the reason why for open ball this is shown with dotted lines, y equal to epsilon. So all those functions which are enclosed within this y equal to epsilon, I mean within this band y equal to epsilon and y equal to minus epsilon, all these functions are basically member of this ball, member of this open ball. So if your function is like this, say this one is, this one is f, if your function is this one, so what you will do at each point of the domain, in this you add epsilon, so it will give you f plus epsilon, point-wise addition, f plus epsilon, and subtract, because at each point it will basically denote a real number, so you can do all this. So f minus epsilon, and collection of all these functions which lies within this band will be the member of the ball with center at f and radius epsilon, So you can see that again, if you look at the boundary of this one, this ball may be convex. I mean, strictly this is not strictly convex in general. Okay. Now, so what we have observed so far, that the usual norms on Rn, for example in R2 we have seen for n equal to 2, is strictly convex. Usual norm, I mean Euclidean norm, as is any one of the and norm 1. Look, the norm 1 and norm infinity, this is the infinity norm and norm 1. We have the balls of this type in R2, and rhombus type, and this infinity we have the balls of this type. So you can see that these norms are not strictly convex. These norms of ball are not strictly convex, and but if you change the norm, we will find that best approximation may not be unique. So we have seen several of the examples. One more example, last example I want to state here. Suppose in x equal to R2, we have this norm of x y equal to maximum. Actually, this one is your norm infinite, maximum of the component x, mod x and mod y. And consider this, here I have changed the subspace 0 y belonging to R. So you can see that this is basically the y-axis, this is 0 y, this is your subspace 0 y. And let us take any point x equal to 1 0 belonging to R2, any point 1 0 R2 here, 1 0 R2 here. Now what will be the best approximation to this point from this subspace under this norm? Actually this is maximum mod x mod y. This distance will be any point here. We have to move like this, mod x and then mod y. Okay, so one can observe that one can look, see, we know that with respect to this, the norms, I mean by taking the ball this 1 0 at center, if you start looking at the boundary of ball, if you start increasing the radius of the ball, then what will happen, that at some time it will coincide like this. Okay. But also see, in this norm there is maximum, but in definition of best approximation already there is infimum. Outside there is infimum, and inside within this norm we have the maximum. So first you have to compute the maximum and look at all this set, and then you have to take infimum. So what will happen if you take any point here, say half, 0 to half here, then this length will be half and this will be 1. So its maximum will be 1. So in all such cases, maximum will be 1. And infimum, and if you take any point outside here, say this distance is greater than 1 and this one is 1. So in that case, maximum will be greater than 1. So try to compute all such distances and take its infimum. So you will find that its infimum is 1. But that infimum is achieved for all points lying here. I mean from -1 to 1. From -1 to 1. So you can, by visualizing this geometry, easily you can observe that if you start increasing this one, then it will coincide not exactly at 1 point. In fact, it will coincide at more than 1 point. So you can imagine that best approximation may not be unique, and then you can do the mathematical calculations. So you can see that here it is written that infinitely it has many nearest points. In fact, all y lying on y-axis and lying in between -1 to 1 is nearest to x. So there are uncountable number of, see, the best approximation to. So this is what existence and uniqueness in approximation theory. I have given the basic idea. I am not going in detail of this one. Now I will come to constructive approximation. Of how much time I? Okay. Now my question is: can one do approximation in topological spaces? See, in topological space, look what are the tools available in topological space. So if any X is any non-empty set, and suppose script is the topology present on this one, then you can see that how topology is. We already know that topology is first of all you have to write its power set of X, and from this power set you have some collections, say script T, and if phi and X are in this script T arbitrary in union is in T and finite intersection, then this script is said to be topology on X, and once it forms a topology, every member of this set is assumed to be open. So this is what. So we don't. I mean, in general topological space, in arbitrary topological space, we will not talk of distance function unless it is meterizable. Okay. So on this set, we don't have distance function. We don't have distance function in general. So can we talk of approximation in topological spaces? I mean, is there any example? So yes, we can do approximation in topological spaces, and I'm not going in detail of this one. Just I want to give you an example that I say that someone is close to me, best approximation to me if he is working in approximation theory. Okay, so that person may be in some other country. So distance is not a bar, and in fact in topological space you will find that all that homotopy and what we do, all this sort of approximation. Now I will come to the central theme of the approximation theory, Weierstrass Approximation Theorem. So according to Weierstrass Approximation Theorem, for every epsilon greater than 0, there is a polynomial p such that every continuous function can be approximated with this polynomial. And look, this theorem is under infinity norm. I mean, this is not under integral. This one is that you have to fix error, you have to fix tolerance. You have given f for any given continuous function, you have to find this. And as per Weierstrass theorem, for any given function and any epsilon greater than 0, up to this tolerance, I can replace this function by polynomial. Also, it has its trigonometric version, but I am not going to right now do. So there are several proofs. Actually, the basic idea of Weierstrass Approximation Theorem, if you look at the proof of the Weierstrass Approximation Theorem, then with the help of compact support, basically he extended this continuous function on whole R using the definition of compact support, and then by convolving it with the help of Gaussian error function, it becomes entire, and entire you can write in power series, and if you truncate it, you will get polynomial. So that was the basic idea, depending on convolution. But here I want to do its constructive. There are several proofs. But one of the proof, Bernstein, and see this Lebesgue. So I will give you an idea of this proof, that how Bernstein of polynomials, with the help of Bernstein polynomials, how one can approximate every continuous function from CA. Now, what is the basic criteria for doing this? I mean, approximation by algebraic polynomials. So we know that, see, CAB is the space of all continuous function, and Pn, this Pn is collection of all algebraic polynomials of degree at most 10. So obviously, since every polynomial is continuous, so this Pn is going to be subspace of CAB. Pn. Again, here we are taking care of dimension. Now look, we already know the dimension of Pn is n plus 1. N, because the members of polynomial are n0 plus f of the general type n x to the power n, nx to the power n. So it will be generated by the basis 1 x square x to the power n, or you can say that there are n plus 1 free parameters. So its dimension is going to be n plus 1. Now, so what we need that if you observe at Chebyshev problem, that we need to approximate this f by p. So in this norm, in this sup norm, already maximum is there, and then we need to take its infimum. Actually, there is a difference between maximum, minimum, and supremum infimum. Maximum, minimum, whenever exist, will be member of the set, whereas supremum, infimum may or may not be member of the set. So if your space is closed, then either you write minimum or infimum. That is not a problem. So if suppose this one is this minimization of this maximum of mod of f minus p, because if you write norm of f is equal to supremum of mod fx, and from norm of x minus y equal to d of xy, using that you can write this one as d of. So what will happen that what is the basic criteria for observing how to get a p? Actually, I want to say that how to construct a p which is within this epsilon tolerance, which will and approximating this f. So for that we have to use the limiting criteria. First of all, we have to look at some subspaces which have finiteness in the terms of say dimension, depending on the problem. So what we will observe here that suppose Pn star is okay. So for this Pn, suppose this is the ENF, also called as, you can say that error because we are approximating f this f by p. So if we start increase the dimension to get a polynomial which approximate f within that epsilon bound, epsilon tolerance, so you need to increase its dimension. So obviously this en plus 1f will be less than equal to f. Why? Because see, if your p is coming from Pn, polynomials of dimension at most n, dimension n plus 1, or polynomials of degree at most n, and if you increase your space, let us choose p from space of polynomials of degree at most n plus 1, then obviously this en plus 1, this term will be at least either equal to this one or either equal to this one or less than, because there may be some element from Pn plus 1 which approximate better than the previous element. Okay, so and this Pn plus 1 is already going to contain the members of Pn. So in this way, what is going on, that if we keep on increasing the dimension, I mean this epsilon, or say en plus 1f, I will get a polynomial, I will get a dimension of the subspace from which I can get this polynomial. Now how to construct that polynomial, that is a different, that we will see. One of the example I will state with the help of Bernstein approximation, Bernstein type. So we have to use the limiting argument that try to choose a subspace having finite dimension, because for implementation we need finiteness. There is also PAB, but we are not going to do it. In fact, PAB is not intense in CAB. You can choose a sequence of function like 1 plus x square and so on, and it is converting to e to the power x, which is not a member of PAB. So you can. So the basic idea is that here, by the limiting argument, this error is going to be minimized. Now I would like to state one of the relation between measure of the error under 1 to an infinity norm in CAB. Actually, this fx minus px, if suppose we need to minimize this greatest error. So there is a result that if you compare in CAB with respect to the infinity norm, with respect error with respect to two norm, your Euclidean norm, least square error norm, and this with respect to integral norm in CAB, then this is the relation. If you take b equal to on closed interval 0, 1, basically this is on closed interval AB. So if I take b equal to 1 and a equal to 0 on closed interval 0, 1, then you can see that norm of E1 is less than equal to norm of E2 is less than equal to norm of E infinity. So norm of under integral norm and least square norm, those norm has to be either cannot exceed the infinity norm, cannot exceed the infinity norm. However, converse need not be true. So for that, I would like to state one of the function here. Suppose we are interested in finding the error in approximating this constant function fx equal to 1 from this set where lambda is some positive parameter. So if you look at the integral norm 1 and this 2 norm and infinity norm, so you can clearly one can do this computation. I am emphasizing more on the logic here. So you can see that if lambda tends to 0, then this term is going to 0, this term is going to be 0, but this is the same because it is independent of lambda. So if supremum norm, if infinity norm is less, then norm 1 and norm 2 has to be less, but its converse need not be true. So what application it has? So you can look at that here, that in order to develop algorithms that gives approximation with small errors in the 1, 2 and infinity norms, we just have to ensure that the algorithm is suitable for the infinity norm. The infinity norm is sometimes called the uniform or minimax norm, and the 2 norm is sometimes called the least square or Euclidean norm. Because if your error is less than infinity norm, then norm 1 and norm 2 will be always, cannot exceed the infinity norm. So this is the relation between those norms. Now, how to do? Let me give you idea of this. Actually, Bernstein, Weierstrass said that every function f, every continuous function f can be approximated by polynomials up to desired accuracy. Okay, up to desired error. But the problem is that how to construct that polynomial. So Bernstein in 1912 constructed this polynomial. Actually, he divided this 0 to n in 1 to discretize this. And if you want to parameterize this any interval on C 0, 1, then you have to divide it by n, 0 by n, 1 by n, 2 by n. So here basically k is running from 0, 0, 1, 2, 3, n. K is running from 0 to 1, and f of k by n is basically a real number. So you can think basically what he used that for the constructive proof of well-known Weirstrass Approximation Theorem, he used probabilistic approach. See, Korovkin Theorem came in 1950, after almost 38 years after this, and they used different approach. But the Bernstein is based on probabilistic approach, and its uniform convergence can be proved using the Chebyshev law of version and that uniform continuity. Using that, one can do one can show that it will converge uniformly to any given function f. So here I just want to give you an idea that how to construct Bernstein polynomial, and I will tell you the reference from which, if anyone is interested, you can read it. So actually, what is the logic behind construction of this? You know that basically this Bnfx is expectation of the function f. So the idea of constructing this polynomial, you know that the weighted average is given by this formula w1x1 plus w2x2 plus wnxn upon say w1 plus w2 plus wn. So we are assigning weight w1 to this real number x1. So if you suppose in tossing of a coin, this can be also phrased in tossing of a coin or that confused state movement left to right, that I will explain. So what will happen that to each real number, for k equal to 0, see when you toss a coin, in tossing of n coins, the number of heads, getting exactly k heads is given by nc k x to the power k into 1 minus x to the power n minus k. And basically this one is a real number, this one, because for each k, whatever function, if you put this value, you will get a real number. So for k equal to 0, you can just imagine it as that we are getting this one as in a game of coins, either we loss or gain. This much amount we have to pay, f of k by n. So you can visualize that for k equal to 0, we have nc 0 x to the power 0 into 1 minus x to the power n minus 0. This one is the of getting exactly 0 head. and we know that the total sum of probability is 1. So what will happen that for this nck x to the power k 1 minus x to the power n minus k, its sum for k equal to 0 to n will be 1. Why? Because if you look at the binomial expansion, this is basically expansion of x plus 1 minus x to the power n. Okay, so you will have 1. So for this k equal to 0, let us suppose that this one is x1. We are assigning it the value nc0 x to the power k 1 minus x to the power n minus 0. Then for k equal to 2, we are assigning nc2 x to the power 2 1 minus x to the power n and so on. And this whole term will be 1 because this is the sum of this probability. This is 1. So this is the way you can visualize this operator, and it comes out to be expectation of f using law of large number, and it can be also viewed as convolution by taking composition with the function, I mean this p and x as 1 minus x with g of x. So there are some, if we put f equal to 1 here, if you put a function as 1, I will get bn of 1 equal to 1, and it will show you that total probability will be 1. And for bn x, it is equal to x. Actually, this will compute to mean, because already here I have divided by n. So if you will not divide, you will compute and want to try expectation of this one. So you will get the term nx or np in binomial, just like we used to do. So if you divide it by n, so second, if you put f equal to 1 here, you will get the mean, and the third will give you the variance. So what we are doing actually, its mean is k by n, and it has its geometrical application. I mean, if you are choosing, okay, let me start first this diagram, then it will be more clear. Actually, the idea behind this is somewhat. Bernstein's proof is a discrete analog of the Weierstrass original proof. Here, continuous diffusion is replaced by a random walk, made precise by the notion of idea of Bernstein polynomials. The law of large numbers and the uniform continuity of f are responsible for the fact that this approximation is uniform. So to do this approximation, to show this approximation is uniform, one needs the following lemma. I mean, all these properties will be useful. And why these properties are used? Because we know that expectation is some kind of theoretical average, and it is the mean over entire population. So if your sample space, suppose this one is mean of your sample space, and each of them x1, x2 has finite expectation, then for n, this sample mean will converge to true mean. So based on that idea, we call law of large number, and in probabilistic sense and in almost sense, strong law of large number. Basically, here Bernstein tried to build this operator, and there is one more result, Markov inequality. And according to this Markov, this is the relation which gives you the relation between expectation and probability. And it says that that if expectation is less, then probability has to be less. There is also Chebyshev version, which I have not written here. So what we are getting here is that, actually the problem is that probability functions are easy to deal when we have one or two random variables. When dealing with very large numbers, better to take limit. So by taking limit, sample mean converges to true mean. So this is the idea of using the law of large number here. The over probability convergence, strong law of large number. So using this, we already know. Let me give you an overview of this result. See, operator here, basically operator is function acting on the space of function. Let me state here. What is going on? See, look, this Bn. I have taken this notation. Actually, this Bn, this operator is acting on functions, and for function the domain is 0, 1. Okay, because we have restricted on 0, 1. So this Bn is acting on function, and for f we have x. So in this way we are using this notation. So what is going on here is that we know that this one is expansion x plus 1 minus x to the power n, and we already know that this sum is 1. And if we replace this f1, actually there is a theorem for positive linear operator, and according to that, Okay. So if I take f1 equal to f1 basically f1 is 1 here. F1 is equal to 1. So on taking f1 equal to 1, uh, okay. Actually your function is in Bernstein operator. Look the right hand side we have the function as f of k by n. F of k by n. And if your function is say f of 1 equal to 1 constant function, then this f of k by n will be equal to 1 and you will get this one. The total sum is equal to 1 because here we have f of k by n in construction of Bernstein operator, and if this becomes 1 then the first you will get the first result. If I choose f of x equal to x, let me take the function as f of x equal to x. So by this logic f of k by n will be k by n. So f of k by n becomes k by n, and if you simplify it you will get x. And if you multiply here earlier n, you will get the mean nx. So these are the computation which I am not going to discuss here. And if you take f2 f of x equal to x square, then you will have k by n whole square, and after simplifying you will get this one. So you can see that Bernstein polynomials are not interpolating this x square. Why? Because it is not giving exactly x square. However, if n tends to infinity, it is going to converge to x square. So we have shown that as f2, one can approximate fx equal to x square by this Bernstein polynomial. Now, since Bernstein, now this k by n minus x square, if we operate Bernstein polynomial on this one, we will get this one. Sorry, k by n minus x whole square. If you multiply this one, then already earlier using result, because in k by n minus x square, we have already this k by n whole square minus 2x into k by n plus x square. So if you operate Bernstein on this one, and cx on this one, you will get this all these results using the earlier one. But what is the basic behind constructing this one? So let me explain this one. Actually, I think it's on next page. This one is the probabilistic interval. Actually, what I want to say that suppose if n is equal to 12 and x equal to 1 by 3, then mean nx will be, in case of binomial, mean nx will be 4. So if you are close to this 4, if your x is, this is basically nx, or say if you are close to this, if your k is close to the k by n is close to this x, this mean, then its contribution is more. And if you are moving away from this mean, then it is going to contribute less. So by taking, so you need to check whether this mod of x minus k by n, this mod of x minus k by n is less than equal to delta, less than delta mod of x minus k by n. So if you multiply this with n, you will get nx minus k. So nx is your mean, and if your k is within the delta radius, then you have to look at all those contribution by all those k and all those k which are lying outside the delta radius. So for that, for contributing that, actually all these results are derived. These two lemma which are written here, that k by n minus 6 and k by n for mod of k by n minus 6 less than equal to delta, and for mod of k by n, look this one, for mod of k by n minus 6 less than equal to delta, this one is the contribution, and for all those k which are lying outside the delta, this one is the result which we will use in the proof. Okay, so actually the basic difference here is that okay, so you now using uniform continuity here, see, I want to approximate this function f with the help of Bernstein polynomial. So for this, I need to, as per definition of convergence, I need to find at least one n naught such that for all n greater than equal to n naught, this sequence of operator, this sequence of polynomial is going to converge this fx. So I have to find this n naught. So for proof of that, what we will do that, see, in this fx, I can write this fx as fx into 1. And 1 as, you can write 1 as summation n ck x to the power k 1 minus x to the power n minus k. So if I replace this one by that one, then there is no problem. Now you can take this term outside. So here I will be left by fx minus f of k by n. Fx minus f of k by n, and just use this inequality because already this is non-negative. N k is already non-negative. X is lying in 0 1. 1 minus x is again will be non-negative. So this is non-negative, so it will come out. And you here actually One can also use modulus of continuity, but I'm not going to do. Now here we have contribution. See, using using uniform continuity. See, any continuous function on compact domain is on closed interval AB is going to be uniformly continuous. So using that, one can show that whenever mod of x minus k by n is less than delta, k by n is less than delta, then fx minus f of k by n has to be less than epsilon for every epsilon greater than 0. So for x minus k by n less than delta, one can use the definition of that uniform continuity. So you will find that for k belonging to f, here you will find that you will get epsilon by 2. Okay, and for k, for all those k which are lying outside the delta radius, you have to use, because you cannot use the uniform continuity there. So you have to use the big law of, law of large number, and from there you will get this one. Because fx minus f of k by n, if you take this norm is basically defined as supremum of mod of fx minus fy. So it is going to be less than equal to 2 times norm f. So using this, one can construct that particular n naught will be basically this one, such that for all n greater than equal to n naught, the sequence of the members of the sequence will start lying in every ball around fx, in every ball around fx. So this is the basic criteria. Using this, it has been shown by Bernstein that this every function can be approximated by this polynomial. Basically, this BNF is a polynomial. And later on, it has also its probabilistic version, but I'm not going to discuss it here. So what we will observe here, that the distribution is concentrated near the mean, and those terms for which k minus nx is large do not contribute much to the distribution. In other words, if n is large, the most likely outcome of n trials is to have roughly nx successes. Thus, the average number of successes in large number of trials is a good estimate for the actual probability of success. So it can also be expressed in, this. Okay, I am skipping that its probabilistic version in terms of points or in confused state walk, that concept. But here, see, after this, around 1950, some mathematicians involving Korovkin. Actually, there were 3 mathematicians who did this at that time. So they said that they proved that not only, since we know that CAB is a space which is not strictly convex with respect to sup norm, with respect to infinity norm. So best approximation may not be unique. So one can construct different positive linear operator, and using that, in here there is a theorem. All those operators are said to be positive linear. See, here t is acting on function, and function for function, this is the domain. So this is the notation we are using. So for all f greater than equal to 0, if t of fx is greater than equal to 0, so we will say that those operators are positive. And linearity, you already know that t of alpha x plus beta y, t of alpha plus beta g equal to alpha t plus beta g. So this is the Korovkin's type approximation theorem for positive linear operator. And according to this theorem, if Tn is a sequence of positive linear operators from CAB to CAB, then one can approximate every continuous function with the sequence of this operator, provided it converges for the test function 1t and t square. Actually, this 1t and t square are called as Chebyshev test function, and depending on the space, one can choose. There is criteria for choosing Chebyshev test function. So here you have to only check these 3 criteria. If your operator converges to these test functions, then with the help of those operators, one can approximate any continuous function. So here you need to just check these test functions. So this is also one of the applications of that extension of, say, Weierstrass Approximation Theorem. Now I would like to, because I have almost 10 minutes, so just I want to give you an idea about some recent work. So if anyone is interested, or their students are interested, so one can contact me. I will email this. Already I have emailed this PPT. So you can see that with the development of Q calculus, actually Q calculus is a generalization of quantum calculus, classical calculus. without limit. So in case you put q equal to 1, if you look at the detail of this one, if you get q equal to, if you get put q equal to 1, you will get all results of classical calculus. So it was Lucas in 1987 who first constructed this rational operator. And look, if you put q equal to 1 here, then it will give you the classical result. I mean classical Bernstein operator. But this one is a rational. And after 10 years almost, Phillips constructed another Q analog of this one, Q analog of this operator. And we already know that CAB is best approximation in CAB may not be unique. So you need to construct different operator and compare the rate of convergence. Okay. So he constructed this polynomial. After 10 years, Phillips constructed these polynomials. And again, see, both the operator given by Phillips and this Lucas, both are different. One is a rational and this one is a polynomial. But both on substituting q equal to 1, they give you this classical Bernstein polynomial. And due to the presence of this extra parameter q, if you look at the detail of this one, then it will provide you the extra flexibility in approximation. And even it has been used in computer-aided geometric design for construction of Bezier curves. And then in 2015, I with my supervisor, Professor Mursalin, and one of my colleague, Khurshid, we have constructed the post-quantum analog of Bernstein polynomial, okay, published in Applied Mathematics and Computation. And you can see that if you put p equal to 1 here, it will become Phillips operator, and if you put p equal to 1, it will give you the classical Bernstein operator. And then actually at that time we have constructed, and we don't have any application, but in 2017, Khalid and Lobial from JNU, basically they constructed this one, post-quantum generalization of Lucas operator, and published in Journal of Computation and Applied Mathematics in 2017. And in this paper you will find that they have used the basis of this operator to construct Bezier curves and surfaces. So after that application, there are now later on we have also given one of application of post-quantum calculus in this compact disk approximation by Lorentz type polynomial in compact disk. So because in computer geometric design, actually computer geometric design is subject which deals with computational aspect of geometric object, and it emphasizes on the mathematical development of of the construction of curves and surfaces. So you know that Adobes, Illustrate, and all these are based on the concept of Bezier curves, and Bezier curves are basically using the Bernstein polynomials. So Bernstein type polynomials has used in this computer geometric design due to the fact that reparameterization of f of k by n, which we have seen. So actually I am not going to history of this one, but there were two scientists named basically this Citron had by French, Castillo had by Citron car company, and this one, second one, Bezier by Renault, and basically they are hired to design curves and shape modeling of cars, and both using Bernstein polynomial. Their approaches are different, but they have given the same result, but their approach are different. One have used this concept. I mean, using the Bernstein basis, one has constructed this. See, any Bezier curve can be constructed using this is your representation. I mean, in terms of computer geometric design, you can call it as control polygon, and writing it as a linear combination of Bernstein polynomials and control polygon, one can generate Bezier curve. And by varying this control polygon, you will get different shape. So this is the idea behind construction of this one. So you can see that these are the control points, and you will get this curve by moving control points here and there. Your shape will change. So that is, he has used a very basic mathematics, but look at its application. It has a nice application. And then now some of the researchers have started also. See, in CAB, we have constructed operators on CAB, and then we have used the linear structure of CAB. I mean underlying field. So if you replace the underlying field with non-linear structure, I mean like fuzzy type operations, then that will give you a pseudo-linear approximation. So in place of field, if you take some semi-ordered rings. So there is a paper by Barnabas, and he has applied this concept in constructing and reconstruction of this image, singles. So there is a question that one can work in this one, that using this all max mean and max product fuzzy type operations, one can apply this for Q operator, because still it has not done, and then one can compare their rate of convergence and all trade-off result with the classical existing part, and with their this pseudo-linear operators without Q. And also, because with this extra parameter Q, we have flexibility in approximation, we have flexibility in parameters, so there is chances of improvement of result. And there is one more result which we as a computer scientist we may use, that is called statistical convergence. This is also a very good area. Reason is that, see, in real life most of the sequences are not convergent, so to deal with convergence of those types of sequences, statistical convergence are used in almost sense. See, in classical sense, we know that convergent sequences are always bounded, but in statistical sense, a statistical convergence sequence may not be bounded. So, due to shortage of time, I have not included in, here the concept of statistical convergence. But if anyone is interested, I can. So here I would like to state that these books. See, the first I will give reference to this one. Those who are interested, Approximation Theory by and Methods by MJD Powell. This is a very good book covering pure as well as its applied part. And then for applications, you can look at this Approximation Theory and Approximation Practices by this Treffer. And for basics of approximation theory, this book is also very good by Karothar. Short course on approximation theory. And for results of pure mathematics from approximation theory, you can follow this book. This one is a very good book by Rusikesh Maskar. And there are several books, but I found this as, and especially if you want to particular study this Bernstein, then you SN proof by Bernstein, then you can look at the book by Lorentz. Especially there in that book various this one Lorentz Bernstein type polynomials by Lorentz in detail about Bernstein type polynomials results. And this is the paper which I was said that Bezier curves based on Laplace post quantum analog of Bernstein functions. And I think I should stop now. And if you have any question, then you can ask. I think I was a little bit fast while explaining. I don't know, but if you because in 1.5 hours one cannot explain everything. So because see. For minimum, one need 24 to 30 hours for explanation of all those concepts. But here, my emphasis is more on giving you the idea of the basics of approximation theory. Even there are parts in which one can include this approximation of discontinuous function. Already, I have not taken that one, like by using Chebyshev interpolants and other methods are there. Okay, so if you have any query, you can. Yes, feel free to ask. Whatever I know, I will tell you. And if I don't know, I will read it again, because you know, mathematics is we are improving every time. When we get some unexpected question, then again we have to read, and this is what a job of a teacher. That basically motivates us to reread, you can say, because in approximation every time we are trying to improve the results. See, we know, most of us are using MATLAB, and you know that to plot fx equal to sin x on 0 to 2 pi, we know that theoretically everything okay, you can plot on whole real line and on closed interval 0 to 2 pi. But when it comes to application, you have to discretize the closed interval 0 to 2 pi or any interval for plotting sin x, because MATLAB cannot deal with, I mean, continuous string. So that one is the basic. So when it comes to application, we have to somewhere use the finiteness. We have to somewhere use the finiteness. And if you increase the number of partition, I mean discretization, those points, you will get a smoother curve. So that is also. So look at the difference between the theoretical existence and when it comes to application. So that is what approximation theory comes. The role of approximation theory is important when we are trying to apply those results. And I have seen some of the lectures. Now I have not attended total lectures, but 2-3 lectures, and all of the invited speakers which I have attended, they have given a very good lecture. The basic idea about I mean function analysis. So for working in approximation theory, you need to have basic idea about real analysis and metric spaces, function analysis. For applied part. Okay, so if you have any question, you have any query, you can ask.
Sir, I think there is no queries from audience side, sir.
Yes.
Okay, thank you, sir, for giving your valuable insights on basics of approximation theory. It will be a great pleasure for us to listen to your talk. Thank you once again, sir.
Okay, thank you very much.
Thank you, sir. Dear sir, ma'am, you can go for break. Next session will start at 11:30 a.m. sharply. Thank you all. Have a nice day. Thank you, sir.